Okay, hello everyone, and welcome to our final presentation for multi-agent debate. This paper is titled Improving Factuality and Reasoning in LLMs Through Multi-Agent Debate. The authors are Du, Lee, Toralba, Tenenbaum, and Mordach. My name is Chaz Merritt, and I'm presenting this paper alongside Sean Patel and Lokesh Adusimili. So let's go ahead and jump in. Just to give an overview real quick, in our last presentation we covered the topic of multi-agent debate as an alternative mechanism to things like chain of thought for improving LLM quality and improving their reasoning. First, we aim to replicate the experiments performed by the original authors to understand the effect of multi-agent debate on popular LLM reasoning benchmarks, such as the GSM-8K and MMLU. Next, we extend on their multi-agent debate framework by fine-tuning a model specifically for multi-agent debate. We elected to use supervised fine-tuning as it's cheaper and less time-consuming than other methods like RLHF. In the original paper, the authors used some clever prompt engineering to encourage the models to be more stubborn or more agreeable, and they found that stubborn models would have longer debates, which in turn slightly improved performance. Based on these findings, we hypothesized that we might be able to improve debate performance with supervised fine-tuning by creating a hyperparameter for stubbornness and agreeableness. After all, you probably wouldn't speak the same way in a debate that you would in a normal conversation. This task turned out to be a little bit harder than we expected. Even though SFT is typically the cheapest option for fine-tuning a large language model, it can still get pretty expensive when working with the large benchmark datasets that we used and that were used in the original paper. So to reintroduce the topic, we begin by framing multi-agent debate in context. It's fairly similar and fair to compare it against other methods like chain of thought reasoning. The driving idea behind all of this work is, of course, the saying, 2 heads are better than 1, or 3 heads are better than 1. This motivates all of multi-agent debate and the core idea that if we can have multiple instances of an LLM talking to each other, then we might get a better output. So multi-agent debate is, of course, about instructing the agents to argue against other answers and defend their own before they can give a response to the user. This response is intended to be the consensus of the agents in the debate, but there's no real way to guarantee that a consensus is reached. In this case, the response is decided by a moderator who is meant to independently observe the debate between 2 agents. And in actuality, this is why 3 agents is often used so that a simple voting system can be used to decide on an answer in case there's still disagreement after the debate. There are many obstacles to multi-agent debate. Most of all, it's very expensive and slow. Each agent has to respond to multiple rounds of debate, and then the consensus answer has to be given by the moderator. Imagine doing this for every question you asked an LLM. It would take ages and cost a fortune. That's why the authors only did a max of 3 rounds of debate. Critically, multi-agent debate doesn't always outperform single-agent chain of thought despite the extreme spike in expense. It performs well on some benchmarks and poorly on others, but often it achieves about the same performance. There could be many reasons for this. One idea is model homogeneity, which is connected to the notion of a model being agreeable. If you've used LLMs for a while, like I have, you're probably all too aware that they can act like yes men sometimes. They will almost never disagree with you, even when you say something that is completely ridiculous. I've seen people asking ChatGPT if they should make a business selling actual literal trash, and it applauded the idea as being avant-garde and subverting expectations. This behavior in turn carries over into our debates, which makes them worse at defending their own positions. I've linked to this other paper here by Zhang et al. Titled If Multi-Agent Debate is the Answer, What is the Question? If you're interested in exploring more about multi-agent debate, I would encourage you to look at this paper. They go deeper into the limitations and explore some ways to alleviate them by interjecting more heterogeneity by including access to multiple foundation models and a single agent. So some of the actual methods of the paper themselves are also somewhat limited, and we sought to address these limitations as well, just by replicating them with modern models and using increased context length and even more advanced models that include chain of thought itself. So this paper was published in 2023, but most of the work was done in 2022 or earlier. This means they used older models like 3.5 Turbo, which has a context length of only 16,000 tokens. And this makes multi-agent debate very difficult because, as we already mentioned, it takes a lot of tokens to get through multi-agent debate. For comparison, the models that we use, 4.1 and 4o, have context lengths up to 1 million tokens. Additionally, MAD draws comparisons to chain of thought as an LLM improvement, which makes sense. They're both somewhat based on prompt engineering. And in the paper, the authors state that multi-agent debate with chain of thought improves performance by roughly 5% on the benchmarks. But chain of thought itself has come a long way since GPT 3.5 was around, and would likely be even more performant today due to the quality of the models and its widespread integration.
So we had implemented the similar kind of experimentations on a couple of data sets, which are GSM-8K and MMLU. So coming to the GSM-8K, it's basically a middle school math data set where it would contain a bunch of verbal questions, and the answer would obviously be a numerical answer. And coming to the MMLU, which stands for the Massive Multitask Language Understanding data set, which has been popular since a while. So it is basically a data set which has diverse sets of domains, 50 plus odd domains, and a bunch of general knowledge subjects too. And it's basically a multiple choice question answer type data set. So both of these data sets are used in the base paper, and we had also implemented them on our implementation too. So our testing had included 100 test samples, and we necessarily don't need any train samples, as it is a zero-shot inference from the large language model's perspective, and we don't need to do any kind of pre-training or any stuff of such sort. So coming to the setup that we had implemented, we had a couple of agents from Gemini and ChatGPT, which are the state of art from both organizations. And coming to the round zero, it's basically a zero-shot inference from one of their models. So it would serve as a single model architecture. And coming to the multiple rounds or multi-agent debate protocol, so the agents would receive their own prior self answers and their peers' answers or corresponding models' answers. So based on their previous answers and the corresponding models' answers, they would compare and contrast the answers and try to come up with the new set of answers, which would go on for debate for another round until a threshold. And coming to the optimization, we had implemented early stopping, where if a model or a bunch of models had come to a conclusion beforehand of the threshold, then we would abort the debate process as they had met to a conclusion or consensus. And for the aggregation, if at all the models were converged, then we would consider the converged answer as a final answer. And if not, then we would consider the ensemble method, such as the maximum number of models or majority in this case. So for the matrix, we had calculated the accuracy along with the convergence rate, which accuracy is being comparing with the aggregated letter or the final answer with the ground truth, and convergence rate is the percentage of debates where the models came to a identical answers or same consensus. So coming to the numericals or benchmark comparisons, the paper had implemented the grade school math and MMLU as we had it. And it's basically back in May 24. So it's basically an year ago when it's published, and it might be an year and a half ago when they had implemented all this stuff. So in the recent times, it's a fast moving space, and there are a lot of advancements in the field. So it's pretty hard to compare the baseline models from May 24 to the models of current day, which is somewhere around 14 months, I guess. So coming to the single agent, they had achieved around 77% of accuracy from zero-shot inference, where we had achieved 98% in our implementation from Gemini 2.5, which is the currently best reasoning model and state of art. And coming to the other sorts of models, where they had individually implemented the reflection, majority, and debate, where we had aggregated everything into one, where we had implemented the multi-agent debate along with the self-reflection and chain of thought into one single experiment, as we are resource constrained. And for that, we had achieved around 93% of accuracy, which might require further fine-tuning and temperature settings and prompt settings, which again, we are resource constrained, so we didn't have chance to do it multiple times. And coming to the convergence rate, we had achieved 94% of convergence rate, but still we had only achieved 93% of the accuracy, which strongly indicates that even though models converge at a point, it doesn't imply that it is the final answer. And coming to the other data set, they had also implemented the MMLU. So we had implemented the MMLU computer science domain for 100 samples. So this could be a good sample set for averaging and aggregating stuff. They have got an accuracy of 63.9%, where our zero-shot inference from Gemini 2.5 got 97%, which is incredible. And coming to our multi-agent debate with a self-reflection and chain of thought, we had achieved around 98%, where in this case, we are a bit lucky with the fine-tuning and hyperparameter setup. And coming to the convergence rate, it's only 96%, but still we had achieved 98%, which means that even though models might not agree on the same page, there is quite a chance that few of the models at least would be correct in their answering. So again,
Thank you, Lokesh. Now moving on to addressing the previous questions. So as we posted our last post, we had a lot of feedback on the multi-agent debate framework itself. One of which from Emma said that, hey, will ChatGPT just admit that X is correct even though Y may be correct? Or Tyson Jordan saying that, is there more pushback if the model knows it's trying to reach a consensus? And lastly, Kavya said, well, what happens when one agent provides a really well-structured argument, but it's in fact correct? And we came to the conclusion that this all falls upon a metric we call agreeableness. Now, this agreeableness, we wanted to fine-tune our GPT-4o mini model and basically say, hey, if the prompt has an agreeables level of 1, we don't want it to agree at all. And if it has a 10, we really want it to agree. And this metric basically allows us to have a hyperparameter to control how willing an agent is to succumb to other influences. Now, in order to super fine train the model, we have to first set up our data, which Chaz will show next.
For data preparation for supervised fine-tuning, we download and sample 5,000 questions from the datasets used in the paper, and these are the MMLU and GSM8K datasets primarily. Then we used the OpenAI batch API to collect answers to these questions while instructing the models to act more or less agreeable. This allowed us to create labeled datasets for supervised fine-tuning where we had the prompt, the debate response, and a flag signaling high or low agreeableness. We also experimented with using continuous values to represent agreeableness as well, where we'd have a value of 1 through 10, denoting how agreeable or stubborn a model response should be. In each case, we put extensive work and compute resources into generating large annotated datasets for supervised fine-tuning, processing close to 3 million tokens for just 2 of the large datasets, benchmarking datasets at multiple different agreeableness scores.
Now on to the demo. But before we jump into that, I want to quickly talk about what super fine-tuning is. And super fine-tuning is taking a pre-trained model, in our case is GPT-4o-mini, and using our custom data to fine-tune and iteratively adapt the model to have an output that's more in line with what we're aiming for. And in our super fine training model, we had 500 rows of data and 100 rows for validation. Our hyperparameters were using 4 epochs, the batch size of 16, and a little high learning rate of 0.1. And ultimately, after the model was fine-tuned, we trained almost 1 million tokens. Now, to show the actual model itself, we have this little toy problem where we have a problem where it says the chicken soup underscore, basically to complete the question or to complete the sentence. And agent 1 in the previous debate is saying, hey, the answer is a book of 101 stories. And agent 2 is saying, this is a delicious soup. Now, we're going to be comparing our super fine-trained model, this B, compared to A, which is just the normal GPT-4o-mini. And let's see what the two outputs are. When on the left-hand side, we have an agreeable score of 10, meaning that it's always going to listen to agent 2, and 1, where it's always going to be listening to agent 1. Let's see. And to no surprise, as you can see in A, it's really only listening to what agent 2 is saying, given our agreeable score. And in case B, it's only listening to agent 1, giving way to our agreeable score of 1. Looking at the actual analysis of our super fine-trained model, we can see that our loss wasn't too impressive as our dataset was artificially created, and we ultimately had a valid loss of 0.5. And in terms of our accuracy, on the validation set, we only had 0.82 accuracy. But this goes into our conclusions and future directions. Just to wrap up our presentation, we know that multi-agent debate is a framework to enhance the outputs from just one-shot approach. And we believe future research into this agreeable metric that we showed in our fine-tuned model could not just help this framework, but also frameworks such as mixtures of experts, which is a framework in which there's a chemistry expert or a physics expert that work together to help and give nuanced outputs to very complex problems. Lastly, we know multi-agent debates isn't what is the cut-of-the-line approach right now, but we do believe that it can give very great input on reasoning and factual accuracy to help LLMs leverage their power of debates and consensus among multiple agents. Thank you so much, and here's the reference in our code.